Hello to my trigonometry pre-calculus classes. Happy Tuesday. I'm sorry that I'm not able to be with you today, but I think we can get this lecture accomplished using this recording, and so let's see how we do. When I introduced lesson 2-4 on the zeros of polynomial functions, we were on pages 119 and got as far as page 121. And we reviewed polynomial long division and practiced finding quotients and then learning how to properly represent them along with remainders in the numerator of a ratio with the divisor in the denominator. And then we learned about the rational zeros theorem. And the rational zeros theorem says that all the rational real zeros of a polynomial are going to be made in a fraction that is created from the integer factors of the constant a sub 0 divided by the integer factors of a sub n. And not only that, but the plus and minus versions of all these fractions. Now what I have for you here is an example that comes from the first example from in the book on this topic here. And one of the things that we have to recognize is that this has to be rewritten. And so we're going to rewrite it. G of x is equal to x to the fourth plus 4x to the 3 minus, and we need actually not minus, but we need a zero term for x squared, because x squared is not represented in the standard form of this polynomial. So minus 12x and then minus 9. So now we clearly see that here are our coefficients of this polynomial. We got a sub 4 is equal to 1, a sub 3 is 4, a sub 2 is 0, and a sub 1 is negative 12, and a sub 0 is equal to negative 9. And here's how we use them. Remember, we've got this p divided by q, and p is made up of all the integer factors of a sub 0, so that's negative 9, and q is just going to be of 1. So this really comes out to be then that our possible values for c are going to be plus or minus 1, plus or minus 9, plus or minus 3. And that looks like it's it, because those are all the fractions that we can form out of a sub 0 divided by a sub 4. And so now what we do is we take the coefficients and we write them like this: 1, 4, 0, negative 12, and negative 9. And then we put our c that we're going to try, like right here, and bring down the 1, multiply by 1, add to the 4, multiply by 1, we get 5, and we add to the 0, we get 5. 1 times 5 is 5. Add to negative 12, we get negative 7. And then 1 times negative 7 is negative 7, and this gives us negative 16, which means we really didn't get it, because that didn't divide in evenly. Okay, let's keep trying, and we're going to do that again. So I'm going to copy this part right here, and let's try another factor. And another factor that might work, let's see if 3 works. How about 1, 3, 7, 3 times 7 is 21, 21, and then 3 times 21 is 63. 63 plus 12, 1, and then 5, and no, that's not going to make it, because that ends up being 153, and when we add that, we're not going to get what we're looking for. But let's try that again, and try negative 3 this time. So we'll copy this down and make that a negative 3. So here's negative 3, and we're going to do it again. 1, negative 3, 1, negative 3. Negative 3, negative 3 times negative 3 is positive 9, and negative 12 plus 9 is negative 3. And negative 3 times negative 3 is positive 9. We did it. And so we found then that negative 3 is a real rational root of this polynomial right here. And so now what we've also discovered is that polynomial can be rewritten like this, that x minus negative 3, so plus 3, times, and now this ends up being the depressed polynomial, and so we take those coefficients as we see them, 1 times x to the 3 plus 1 times x to the 2 minus 3x to the 1 and minus 3. And so that is our factored polynomial using synthetic division. Okay, so where this takes us is we are on page 121, where there is this real-world example 3 in solving a polynomial equation. It goes like this. Business. After the first half hour, the number of video games that were sold by a company on their release date can be modeled by g of x is equal to 2x to the 3 plus 4x squared minus 2x, where g of x is the number of games sold in hundreds, and x is the number of hours after their release. How long, then, did it take for them to sell 400 games? So, because g of x represents the number of games sold in hundreds, you need to solve when g of x is equal to 4. And so, in other words, we're going to try and figure out what x is. So, as you see what they're doing here, they've got g of x is equal to 4 right here, and then they have something that looks like this. So they've got 2x to the third plus 4x squared minus 2x equals 4, which is their polynomial that they said models the number of video games that were sold on the release date. So we change that by setting it equal to 0. That's going to take subtracting 4 from both sides. And what we end up with then is this 2x to the third plus 4x squared minus 2x minus 4. Now, we don't know the answer to what 4 is, but we do know that we can find the rational zeros of this polynomial. And so we're going to go after that. And we know here that a sub 3 is 2, and a sub 0 is negative 4. And so it's going to be some p over q, which is represented by all the integer factors of negative 4 divided by all the integer factors of 2, which is not that hard. So we got plus or minus 1, plus or minus 4, plus or minus 2, and I think that that takes care of all the integer factors of negative 4. Now, those will all be divided by the possibles plus or minus 1 and the plus or minus 2. So as we try to compile then our list of all the possible rational zeros, they are going to be like this. Plus or minus 1, plus or minus 4, plus or minus 2, and then also plus or minus 1/2, and plus or minus, oh, that's it, just because we got 4 halves is 2 and 2 halves is 1, and those are already covered, so we don't need those. And so there's all the possibilities right there. So what we're going to do now is we're going to do synthetic division and take the coefficients and make sure that we have all of them. There's to the third, there's to the second, there's to the 1, and there's to the 0. So we have 2, 4, -2, -4, and our possible C's are all going to go in here like this. I'm just going to copy this because we may end up doing it a few times. And let's go ahead and just use the first one. So we always like to use 1. It's always a good starter. So bring down the 2 times 1 plus 4 is 6 times 1 is 6 plus -2 is +4. How nice. 1 times 4 gives me 4, and when I add that to -4, I got a 0. So since I got a 0, that means that C is equal to 1 is a possibility, and so we can represent it as x minus 1, and then write the depressed polynomial as 2, because of this 2 right here, x to the 2 plus 6x plus 4. And that actually looks pretty tempting because I can pull that 2 out. So let's just do that this way. 2 times x squared plus 3x plus 2. And yeah, I think that that looks factorable. So we can say x plus 2, x plus 1, and there we factored it. So it looks then that this polynomial actually breaks down into binomial factors, linear factors of x minus 1. There's the 2 in the front, by the way. X plus 1 and x plus 2. And so what we end up finding then is that these are the rational zeros. And so 1, 0 is x equals 1 when these equal 0. X equals -1 and x equals -2. So in answer to this question then, as we look at this thing, it's saying how long did it take to sell 400 games? And so here's how we actually look at this, is to say, well, we came up with answers of, I guess we got to 400 games before we started selling them if we use x equals -1, because that would be -1 hours, and -2 hours would be the other answer. So it looks like our answer has to be x equals 1 hour. After 1 hour, they sold 400 video games. Okay, you saw me do example 3 there, and the work is pretty much verified of what I did based on what they did, only, let's see, they divided out the same and ended up with the same result. And so I want you to try now and look at this one called volleyball, a volleyball that is returned after a serve with an initial speed of 40 feet per second at a height of 4 feet is given by f of t is equal to 4 plus 40t minus 16t squared, where f of t is the height of the ball reached in feet, and t is the time in seconds. What times will the ball reach a height of 20 feet? Give that a try. Turn off this video momentarily, and then after the students have had a good enough amount of time, we can pick it up. Okay, so we are asking the question, when is the volleyball at a height of 20 feet? In other words, when is f of t equal to 20, and what value of t will that give us? So we should probably write this in standard form. So here we go. F of t is going to equal -16t squared plus 40t plus 4. And when is that equal to 20? So we're going to do that. And so we got to figure that out. So I'm going to just break this away from the function itself and use that just as an equation. And we'll subtract 20 from both sides. Let's see. negative 16t squared plus 40t plus or minus 16 is equal to 0. So we're going to be factoring this now, only we're going to use synthetic division. And we're going to use, let's see, a p over q, where we're talking about p over q being factors of negative 16 and over factors of negative 16. And so we're looking at 1 plus or minus 1 plus or minus 16 plus or minus 2 and plus or minus 8 and plus or minus 4. So those are all the integer factors of 16. Let's also look at really this same list, and so I could just copy this list and put it down below here. So we'll just do that. So here we go. And we have to list all the possibilities here now. And so all these possibilities. So we're going to start off with this list that we just copied. That's one of them because those are all the ones over 1. But now we have to look at all those over 2. So we're going to go, let's see, plus or minus 1 over 2. And so there's that. Let's see, everything else I think is represented because plus or minus 16 is 8, plus or minus 2 is 1, plus or minus 8 is 4, and plus or minus 4 is 2. So those are all covered. So we got over 2, let's see, are all the over 1, all the over 4s covered? Well, I guess it's going to be plus or minus 1 over 4. 16 over 4 is 4. 2 over 4 is half. We already wrote half. And 8 over 4 is 2. And we already have 2. Okay. But we have to keep on going. And so we have to say plus or minus 1 over 8. Well, that's a possibility. And then also, and we notice that everything else pretty much goes. Let's see, 8 over 16 is going to be 1/2. We already have that one. 8 over 8 is 1. 8 over 4 is 2. 8 over 2 is 4. And 8 over, got all that. Okay, and then finally, it looks like what we have left is plus or minus 1 over 16. So here now is our list of all the possible rational zeros of this polynomial. And I think that it's pretty fair to say that these are all going to be considered. So now what we do is we go with the coefficients, and the coefficients are going to be negative 16, 40, and negative 16. And we start going through it. So let's go with 1. And I think I'm going to go ahead and start by copying this thing again. And let's do 1. So negative 16. Bring it down. Times 1, negative 16. And then add that to 40. That ends up being, let's see, 10 minus 6 is 4. 3 minus 1 is 2. And we copy that up here, 24. And no, we don't get 1 as one of our factors. So let's just go ahead and do this here. We should try negative 1, so let's go ahead and do that. Negative 1, negative 16, positive 16, ooh, that doesn't look so good, 56, times negative 1, negative 56. And we don't get that either because that's not 0. Okay, let's go for the next one. How about 2? 2. No, I shouldn't have done that. Bring down the negative 16, multiply it by 2, negative 32. Bring down, subtract or add the 40 to the negative 32 and get 8. And then 2 times 8 is 16. And yes, we get it. So 2 is an answer. So that's one of the answers. Now we could use the rest of this and just say that that is x minus 2 times negative 16x plus 8. And you see where those those numbers that we get in the result are the depressed polynomial. And if you use that, this is saying equals 0. So we've already got x is equal to 2 from there. And we've got negative 16x plus 8 is equal to 0. So subtract 8. Negative 16x equals negative 8. Divide by negative 16. And look where our answers are now. X is equal to 1/2. And what did this question ask? It said, what times when t is in seconds? So it looks like the answer is 2 seconds and half a second. So at half a second is the first time that the ball is at 20 feet, and at 2 seconds is the second time that the ball is at 20 feet. So I hope you experienced the same result there, and let's move forward. So our discussion has been around finding the rational real zeros of a function. And pictorially how we describe that is that that's where it crosses the x-axis at a rational value of x. And so consider this picture that we're looking at here. We have f of x, and let's just count. All the zeros are going to be 1, 2, 3, 4, 5 possible real zeros of this function right here. And wouldn't it be nice if we could find some value a that's all the way to the left of all the zeros, and this number b on the x-axis that's all the way to the right of all the zeros? That would be this idea of bounding all of the zeros of the function. So one way to narrow the search for real zeros is to determine an interval within which all real zeros of a function are located. A real number a is a lower bound for the real zeros of f if f of x is not equal to 0 in any case where x is less than a. Similarly, b is an upper bound for the real zeros of f if in f of x a value of f of x is not equal to 0 for anything where x is greater than b. And so that's what this is saying, and so if I was to point that out, then anything to the left of this a right here, you're not going to see that function cross at 0. And anything to the right of this b, you're not going to find anything of this function crossing 0 again. And so that's what that means, that we have bounded the zeros of this function between that value of a and b. So you can test whether a given interval contains all real zeros of a function by using the following upper and lower bound tests. Let f be a polynomial function of degree n is greater than or equal to 1, real coefficients, and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. If c is less than or equal to 0, and every number in the last line of the division is alternatively non-negative and non-positive, then c is a lower bound for the real zero of f. So understand that. They're saying alternating non-negative and non-positive, then c is a lower bound for the real zeros of f. And we'll demonstrate that so you can see that. Now, here's the other test. If c is greater than or equal to 0, and every number in the last line of the division is non-negative, then c is an upper bound for the real zeros of f. So, to make use of the upper and lower bound tests, here are those steps. Graph the function to determine an interval in which the zeros lie. Step 2. Using synthetic substitution, confirm that the upper and lower bounds of your interval are in fact upper and lower bounds of the function by applying the upper and lower bound tests. And then finally in step 3, use the rational zero theorem to help find all the real zeros. So let's take a look at this in example 4. Okay, here's example 4, and it's talking about let's use the upper and lower bounds tests. Determine an interval in which all real zeros of h of x is equal to 2x to the 4 minus 11x to the 3 plus 2x squared minus 44x minus 24, and where must those lie? Explain your reasoning using the upper and lower bound tests. Then find all the real zeros. So here are all the steps again. Remember, we're going to graph our polynomial h of x using a graphing calculator. And I've done this, and it's over on the right there in this illustration. So from this graph, take a look at it. It appears that all the real zeros of this function lie in an interval possibly between -1 and below 7. So we're just going to go ahead and say that those are our lower and upper bounds, and we have to test that now. So test a lower bound is step 2 of a value c equals -1 and an upper bound of c equals -7. So here we go, and we're gonna do this. So we're looking now at this c equals -1. The coefficients come from this polynomial up here are 2, -11, 2, -44, and -24. And so notice what's going on now. When you use that value of c equals -1, we're assuming that that could be a lower bound of our polynomial, because there it is right there, -1. So when we do this synthetic division, they call this synthetic substitution, we get this value of 35. But here's what we also want you to see, is that here's a +2, a -13, a +15, a -59, and a +35. That the values of this result are alternating signs in the last line. So -1 then is indeed a lower bound. That's what that test tells us. If you understand how to use the lower bound test, you will see that you'll get alternating signs of positives and negatives. And you even have to kind of understand that business of where it says alternating non-zero, non-negatives and non-positives. So keep that in mind. So we're also testing then a lower bound of c equals 1 and the upper bound of c equals 7. So here's the test for c equals 7. So there it is, 7. And notice that that bottom line now is 2, 3, 23, 117, and 795. All of the values are not negative in the last line. And so, since that's the case, 7 is an upper bound. Continuing with this example, step 3 is to use the rational zero theorem. Now, if we look at our all of our possible rational zeros, remember we have to use the rational roots theorem, rational zeros theorem, and that causes us to take factors of 24 and divide that by factors of 2. So as you look at this list, look at what we have here. We've got, we've got the, there's 9 possible factors here, but it's plus and minus, so we got to multiply that by 2. So there's 18 total ways of doing it. Now, without belaboring it, we'll just go ahead and test some real obvious ones. Like 6 looks like it really was 1, so they test it, and sure enough, we get that 0, and we get a depressed polynomial of 2, what does that end up being? 2x to the 3 plus 1x squared plus 8x plus 4. And so we use that depressed polynomial and look at negative a half on that. And sure enough, we end up with this depressed polynomial again. And then this one represents 2x squared plus 8. And when we pull out that, we factor out that 2, that ends up being this x squared plus 4. So take a look at this now. By the division algorithm then, h of x is equal to 2 times x minus 6, which came from this, times x plus half, which came from this right here, and x squared plus 4. Now, notice that the factor of x squared plus 4 has no real zeros associated with it because x squared plus 4 equals 0 has no real solutions. As a matter of fact, I'll demonstrate that for you here, that if I took x squared plus 4 and said that that equals to 0, we'll subtract 4, and get x squared is equal to negative 4, which means that we're going to be taking the square root of both sides to solve for x, and we're going to see that as the plus minus square root. And you see clearly that this turns out to be plus or minus 2, but that's an I because there's a square root of a negative in there. So it's plus minus 2i, and that's not real. So there's that. And so as we continue on then, they show you that those are all the possibles, and we ended up with only 2 rational root zeros, 6 and negative a half. And the graph then supports this conclusion. All right, so I'd like for you to try on 4a and 4b. So if we could please have the substitute hit the stop button and give you some practice on that. I'd like for you to try to solve for 4a and 4b and determine the upper and lower bound, and then support that upper and lower bound by using the rational zeros theorem. All right, this is the guided practice on example 4 that I wanted you to try. So hopefully you'll get a similar result here. Now, if you take a look at the picture that they provided, this is what I got when I put it on Desmos. And so take a look at some of the things that we see here. We have a 0 and maybe a left bound. Let's say that this is our left bound here. That would be happening at negative 10, negative 11, negative 12, negative 13. So it looks like negative 13 is probably the left bound because I don't think it's turning around to come back and cross 0 again. We can kind of say that because we know that this is a 4th degree polynomial. So the characteristic is that it's not coming back. This one's a multiplicity of 1. This one looks like it has a multiplicity of 3. And so there's 1, 2, 3, and let's just go ahead and select an upper bound. An upper bound here would be 1, 2. I think I'm going to go ahead and say that 2 is the upper bound. So we'll go ahead and say that, and say we think that our boundaries are located at, what did we say to the left there? Negative 13. And the upper bound was positive 2. So let's test those, shall we? We're going to use synthetic substitution. We're going to make sure that everything's represented. We have to the 4th, to the 3, to the 2, to the 1, and to 0. And let's go ahead and grab those coefficients. 6, 70, negative 21, 35, and negative 12. And we're going to go ahead and do the test now for the lower bound, which is negative 13. So here we go, 6. 6 goes down, multiplies by 13. That's going to be 18 plus 60 is 78. And it's negative, so that becomes a negative 8. And we go negative 8 times negative 13. Well, that'll be positive 24 plus 80. 104, so it's 104. 4, and then subtract, or add negative 21 to 104. So 4 minus 1 is 3, and then 10 minus 2 is 8. So I get 83. Well, 83 times 13, that one's going to take a little bit of extra effort here. Negative 13, we're going to multiply. 3 times 3 is 9. 3 times 8 is 24. 0, 3, 8. And we're going to add those together, and we get 9. 4 plus 3 is 7. And 2 plus 8 is 10. And so that's a negative 1,079. Let's see, that was, negative 1,079. And we have to add that to 35. So 35, and that ends up being 4, 4, 1, 0, negative 1, 0, 4, 4. Okay, one more big bad multiplication. 1044 times negative 13. Negative 13. 3 times 4 is 12. 3 times 4 is 12 plus 1 is 13. 3 times 0 is 0 plus 1 is 1. 3 times 1 is 3. And 0 and 1 times 4, and that's just a 1, so we just copy that. And add 2, 7, 5, 3, 1. So this is 13,572, and when we add subtract 12 from that, this ends up being 13,560. And this is what we're trying to look at, is that because the numbers of the last row now are positive, negative, positive, negative, positive, and that they're alternating perfectly, that makes negative 13 a lower bound. So let's do that again then, and we'll use this test and do it for the upper bound. And let's say, what did we get for the upper bound? Well, let's see. I'm going to copy this here. Go ahead and get rid of our circle, because we can't circle it yet and say we've been successful. But we said that our upper bound was going to be 2, so let's just test that. And here's the test for upper bound. Okay, 6 comes down, multiply by 2, we get 12. Add that to 70, we get 82. Multiply by 2, I get 164. And add that to negative 21, I get 3, 4, and 143. And multiply that by 2, that's 286. And add that to 35. 11, 12, and 321. Times 2, 642. And add that to, or subtract 12, I get 0, 3, 6. And look at this. These are all positive numbers. That means this is an upper bound. All right, we're in this discussion of narrowing our search of real zeros by understanding where our lower bound is and the upper bound is. And we just showed you a couple of tests to show lower and upper bound. Well, here's another one. It's another way to narrow the search for real zeros, and it's to use this thing called Descartes' rule of signs. And it gives me an opportunity to talk to you about one of my heroes, René Descartes. So this rule gives us information about the number of positive and negative real zeros of a polynomial function by looking at a polynomial's variations in sign. So you might recognize this from the lower bound rule. So if f of x is equal to a sub n x to the n plus a sub n minus 1, and so on, is a polynomial function with real coefficients, then the number of positive real zeros of f is equal to the number of the variations in sign of f of x, or less than that number by some even number, and that the number of negative real zeros of f is the same as the number of variations in the sign of f of negative x, or less than that number by some even number. Now what we're talking about here is that we're talking about real zeros, including rational and irrational zeros. And so Descartes' rule of signs does a good job of identifying real zeros, both rational and irrational. It doesn't just focus on irrationals, or rationals, I mean. So before we move on, though, we get to admire and love this guy, René Descartes. You guys all know the Cartesian coordinate system. That's that thing where we're using the x-axis and the y-axis, and we can place ordered pairs. You see 2, 3, and -3, 1, and all that kind of stuff. And then also even as we're looking at things like equation of a circle on the Cartesian coordinate plane. This came from this guy right here, René Descartes. Cartesian coordinates describe a position of a point in 2 dimensions by giving its horizontal and vertical locations, etc., etc. But that was all developed by this guy here, the great mathematician, René Descartes. He's also a philosopher, and he's the philosopher that said a very famous quote, "I think, therefore I am." So once again, going over Descartes' rule of signs, if f of x is some polynomial of degree n with real coefficients, then there are 2 parts here. And the first part is talking about the positive versions of the real zeros. So we're talking about x values that are to the right of the origin. And the number of positive real zeros of f is equal to the number of variations in sign of f of x, or less than that number by some even number. And the number of negative real zeros of f is the same as the number of variations of sign of f of negative x, or less than that number by some even number. So remember that that's what Descartes' rule of signs says. Now, with that being the case, let's take a look at example 5. Describe the possible real zeros of g of x is equal to 3x to the 3 plus 2x to the 2 minus x minus 1. Now, if we take a look at the signs of just that polynomial of just plain old g of x, take a look at what we have here. We start off with -3x to the 3, and immediately we change from negative to positive, so that's a change of signs. And then we change back with the next term, with the third term, and so that's another change of signs. So we have 2 changes of signs. So that means that the number of possible positive real zeros are going to be 2, and so that's what that says. Now, if we take g of negative x and then just replace x with negative and then show what its result is, notice how they do that here. With -3 times negative x to the third, that turns into positive 3x to the third, and then positive 2 times negative x but squared, that stays positive. So that doesn't change sign, right? So we got 3x to the 3 plus 2x to the 2. That doesn't change sign because those are both positive. And then we go plus x, that's still not a change, but then it finally changes just once to from positive to negative as we get to the -1. So that's what's going on here, and so let's read what it says here. The original function g of x has 2 variations in sign, while g of negative x has 1 variation in sign. By Descartes' rule of signs, then, you know that g of x has either 2 or 0 positive real roots and 1 negative real zero. So, from the graph of g of x shown, you can see that the function has 1 negative real zero right here, which is really close to negative 0.5, and it has no positive real zeros. So take a look at 5a and 5b here and see if you can use Descartes' rule of signs to figure that out. How many possible real zeros you have of positive and negative. All right, here's that first example. So we have h of x is equal to 6x to the 5th plus 8x squared minus 10x minus 15. Now we're not going to be worrying about the zero terms in this. This is just Descartes' rule of signs applied. So notice we have 6x to the 5th, and as we just kind of traverse across, we've got this. There's no sign change. There is one sign change, and then there's no sign change, and we get to the end of the polynomial. So since there's only one sign change, right here, we get one sign change. So that says, since we were just looking at h of x, at most, one positive zero, or a multiple of 2 below that. Well, there's no multiples of 2 that are less than 1, so we have one sign change, meaning that we have one positive zero. So one positive zero. Okay, now let's look at, here's the second test. We're going to do h of x, except h of negative x, and let's take a look at it now. We're going to say that's the same as saying 6 and in parentheses negative x raised to the 5th power plus 8 negative x squared minus 10 times negative x minus 15. Now, let's take a look at this. If you do negative x to the 5th, that's the same as saying negative 6 x to the 5. And negative x squared is positive, so that just becomes a positive 8 x. And then negative 10 times negative x gives me also a positive 10 x, and then minus 15. Now let's count. Well, here's one sign change right away. And then no sign change, no sign change. And then here's another sign change. So there's two sign changes. And since we were checking that out on h of negative x, now we're talking about how many negative zeros. So 2 negative zeros or 0 negative zeros. Those are our choices. So I graphed this on Desmos, and so let's take a look at the result here on Desmos. And if you look carefully, here's our x-axis right here. And our x-axis crosses once on the graph, so and it's past positive 1, so there's one positive real zero. But if you look to the left, there are no negative zeros, and so that's consistent with what Descartes told us, because Descartes says the number of sign changes that you have in h of x determines how many possible positive real roots you will have. And you know, if it was like 2, then we could have had 2 or 0, but we had 1, so there had to be 1. In h of negative x, that one helps us to determine by the number of sign changes it has of 2 or 0. So 2 negative zeros or 0 negative zeros. Here's 5b. We have f of x is equal to negative 11x to the fourth. And so let's go ahead and just do this one. Right away, this has a sign change right here. So this is just looking at f of x. And there's a sign change, then not a sign change, then a sign change because it goes from positive to negative. And then it goes straight back to negative to positive. And so here we go. Here's a case now where we have 3 sign changes. And 3 sign changes on just f of x says that there are 3 possible positive real zeros. So I'll just say zeros. Or minus 2 would be 1 positive zero. So now we know how many positive zeros there could be. And then f of negative x is going to be negative 11 negative x to the 4 plus 20 negative x to the third plus 3x, sorry, that's a negative x, to the 2 minus negative x plus 18. All right, we're looking at f of negative x. This turns this into just negative 11x to the 4 because negative x to the 4th power is going to be positive x. This one's going to be a negative 20 x to the 3 because negative x to the 3 is negative x. So that negative comes to the front. So plus 3 negative x squared is positive x. So this just becomes positive 3x squared. And then negative is positive x and plus 18. Now let's count. The sign changes. Well, no sign change. Whoops, don't mark it then. Yes, a sign change, so there's 1. No sign change, all the way to the end. So there's only 1 sign change. Meaning, since we're looking at f of negative x, 1 sign change indicates 1 negative 0. And so here we go. We could have 3 positive zeros or 1 positive 0 and 1 negative 0. So let's take a look at the graph here. Well, it looks like here's our x-axis. And our x-axis seems to indicate that there's only really 2 zeros. One of them is negative, and that covers the 1 negative. That's okay. And we got one of them that's positive, and that covers the positive 1. And you see, up here is where those other ones are. You know, the 2 that they were talking about. So just showing you that, and there we go. The graph supports exactly what Descartes' rule of signs tells us about f of x. So where this is taking us is this idea of complex zeros and something called the Fundamental Theorem of Algebra. So this says just as quadratic functions can have real or imaginary zeros, then polynomials with higher degrees can also have zeros in the complex number system. This fact, combined with the Fundamental Theorem of Algebra, allows us to improve our statement about the number of zeros for any nth degree polynomial. So here's the Fundamental Theorem of Algebra. It says, a polynomial function of degree n, where n is greater than 0, has at least 1 zero real or imaginary, in the complex number system. A polynomial function of degree n has exactly n zeros, including repeated zeros, in the complex number system. And so I want to also apply this to say that when we're talking about complex ones, since they're not real zeros, I'd like to call them roots. And so when we're talking about complex, we'll call them roots. When they are real, then we will call them zeros. So that's just kind of a little thing that I like to say, because this thing was really called the rational roots theorem, that first one. And so let's just keep on moving here. It says, by extending the factor theorem then to include that both real and imaginary zeros and applying the fundamental theorem of algebra, we obtain this thing called the linear factorization theorem. Now, if f of x is a polynomial function of degree n is greater than 0, then f has exactly n linear factors. Linear factors meaning binomials of degree 1. That's a linear factor. So you could have a coefficient a sub n times x minus c1, x minus c2, x minus cn, where a sub n is some non-zero real number, and c1, c2, all the way to cn are the complex zeros, including repeated zeros of f. And when we say repeated zeros, we're talking about, zeros that have a multiplicity greater than 1. So according to the conjugate root theorem, there's another theorem that we need to make sure we understand. The conjugate root theorem says when a polynomial equation in one variable with real coefficients has a root form of a plus bi, where b is not equal to 0, then its complex conjugate, a minus bi, is also a root. You can use this theorem to write a polynomial function given its complex zeros. So let's take a look at example 6. Find a polynomial function given its zeros. Write a polynomial function of least degree with real coefficients in the standard form that has -2, 4, and 3 minus I as zeros. Now, because 3 minus I is a 0, and the polynomial is to have real coefficients, you know that 3 plus I must also be a 0. So using the linear factorization theorem and the zeros, -2, 4, 3 minus I, and 3 plus I, you can write f of x as follows. Now, follow carefully here. It says f of x is equal to some a, and x minus -2, x minus 4, x minus 3 minus I, and x minus 3 plus I. So while a can be any non-zero real number, it's simplest to just let it be 1. And so we write the function then in standard form like this. And go ahead and resolve those negative negatives. And so you've got 1 times x plus 2, x minus 4, and then x minus 3 minus I, and x minus 3 plus I. When you multiply those together, you end up with x squared minus 2x minus 8 times x squared minus 6x plus 10. And when you multiply those two quadratic trinomials together, look at what you end up with is a polynomial of degree 4, x to the 4 minus 8x to the 3 plus 14x squared plus 28x minus 80. Therefore, a function of at least degree that has -2, 4, 3 minus I, and 3 plus I as zeros is f of x is equal to x to the 4 minus 8x to the 3 plus 14x squared plus 28x minus 80, or any non-zero multiple of f of x. So you give it a try. Do 6a and 6b. And we'll stop right here and let you practice. So as we do 6a, we have zeros located at -3, 1 with a multiplicity of 2, and 4i. And by the conjugate roots theorem, we know that also -4i is also going to be a root. So we can write this then. We can say x minus -3 times 1, x minus 1, and we'll just go ahead and say, since that has a multiplicity of 2, call that squared. And then we have x minus 4i and times x minus -4i. We can do that, and then let's just go ahead and straighten it out, get rid of all those negatives, and so we got x plus 3 times x minus 1 squared times x minus 4i times x plus 4i. Okay, let's watch how this goes. We know that this x minus 1 becomes, when we square it, is x squared minus 2x plus 1, and that times x plus 3. And we also know that this is x squared minus 4i squared. So 4i squared, we know, is going to be, well, let's put that minus sign out here, 16 I squared. But we know that I squared is -1, so -16 times -1 is +16. So that turns this into x squared plus 16. That's going to be times x squared minus 2x plus 1 and x plus 3. So we have to multiply that, and I'll go ahead and do the x plus 3 times the x squared minus 2x plus 1. And I'll just use distributive property. Watch how this goes. X squared times x plus 3 minus 2x times x plus 3 times plus 1 x plus 3. And that times x squared plus 16. Let's see. X to the 3 plus 3x to the 2 minus 2x to the 2 plus 6x plus x plus 3, and that whole thing times x squared plus 16. We can clean this up a little bit. We've got 3x squared minus 2x squared. That's just x squared. So we've got x to the 3 plus x squared. And then we've got 6x plus x plus 7x plus 3. And that times x squared plus 16. Almost there. Distribute the x squared first. We got x to the 5th plus x to the 4th plus 7x to the 3rd plus 3x squared, and then plus 16x to the 3 plus 16x to the 2 plus, let's see, 16 times 7 is 70 plus 42 is 112. And that's x. And then plus 48. Because 16 times 3 is 48. Let's see, is there any more cleaning up to do? Yes. 7x to the 3 and 16x to the 3 become 23x to the 3. We've got 3x squared and 16x squared give me 19x squared. I've got a x to the 5 before that and plus x to the 4 before that. And we have 112 plus 48 is 0, 1, 2, 6, and 1, 160. 160. And there we are. There is our polynomial, what did they say, right? A polynomial function of at least degree with real coefficients in the standard form with the given zeros. Now, the other one, 6b, is, let's see, 6b is going to be 2 root 3, negative 2 root 3, and 1 plus I. And I'll copy this and move it to a space where we can work. So I'll cut it, bring it down here. And this is going to be then 1 plus I, but that means that there's the presence of 1 minus I. So this looks like I have 1, 2, 3, 4 roots, meaning it's going to be x to the 4th. All right, so here we go. We have x minus 2 root 3 times x minus negative 2 root 3. And then that times x minus 1 plus I times x minus 1 minus I. Okay, let's deal with the right first. And I think what I'll do is I'm just going to go ahead and put these parentheses in. And that changes things a little bit, but you'll see how that it unchanges as we do it. But this ends up looking like this. X squared minus, and then when we multiply these conjugates together, we end up with something that looks like this. 1 squared minus I squared. So 1 squared is just 1, and I squared is negative 1, but it's minus I squared, so it's plus 1. And so it ends up being 2. And so we got x squared minus 2 is what this whole thing boils down to. All right, so there's that. And this guy, by the way, is also a difference of squares, so we can say x squared minus, because this is plus right here of the minus minus, 2 root 3 squared is what that ends up being. And so this ends up being x squared minus 4 times 3 is 12. So there that is. And as we pull this all together, then we just have to use FOIL here to bring these together. This ends up being x to the 4th minus 2x squared minus 12x squared, and then negative times negative is positive 24. And to finish it off, we just combine the like terms in the middle. X to the 4th minus 2, not 2, 14 x squared plus 24, and we're done. There is our least degree polynomial containing these zeros. Okay? So I think I'm going to stop right there. And here is the part 2 of the lesson 2-4 homework. It's page 127. And do the problems 19 through 25 odd. Do all of those, and then do 27 through 31 odd, and recognize that what that question is asking is that you use Descartes' rule of signs. So determine those zeros according to that. And then do 33 through 41 odds. And I'll be seeing you on Thursday.